Yes, thanks, Mark, for this kind introduction, and also thanks for giving me the opportunity to present our work here. Yes, so this work, the perturbative Ricci-flow in gravity, has been on archive now for about 2 months, I think. And it's like some work I've done with my collaborators, Robert Harlander, Jonas Kohn, and Henry Wertenbach. And yeah, so of course, the basic starting point of this is quantum gravity, as you probably all expect. And so in this talk, I will mostly focus on Einstein-Hilbert gravity without the cosmological constants. So we just have a simple action like this with 1 Newton's coupling. And this is where we'll apply this Ricci-flow to. And like, we'll see what I mean with that. And but like first, of course, I just want to like recall a bit what we know about this action, like the standard folklore that we know about quantum gravity like this. And of course, we all know that there's a slight issue with this action if we try to quantize it in quantum field theory, and that's originating from the fact that Newton's coupling has a negative mass dimension. So in 4 dimensions, it has mass dimension -2, and therefore it is not Dyson renormalizable or power counting renormalizable. And what I mean by this is that if you go to higher loop orders in perturbation theory, new and new operators are induced as UV divergences that have to be renormalized by including new operators in the action. Of course, at one loop, we know that this is actually not happening yet in this sense. And this is because at one loop, only off-shell UV divergences are induced, if you forget about the topological Euler topological term, of course. And so at one loop, I can remove actually all of my UV divergences without including any new operators in the action, just by doing some sort of field redefinition of this form. So I take my metric and I add to it terms that look like the Ricci tensor and the Ricci scalar times the metric. And this is enough to like remove the UV divergences that you encounter here. But of course, in two loop on this breaks down, and this gives us the famous Gaussian term, which is this Riemann cube term, and we cannot remove this anymore by some sort of field redefinition, and we have to therefore include it as an actual coupling in the action. And with this, of course, we know that like a traditional perturbative formulation of quantum gravity doesn't work this well anymore, at least in the UV, because then we have, of course, I mean, this starts a two-loop that you need new counterterms in the action, but there will be even more if you go to higher loop orders, and therefore you have more and more independent couplings that are a priori undetermined, and therefore predictivity breaks down in some sense. But of course, we're all here because we're interested in asymptotic safety, and asymptotic safety actually can give us a mechanism by which we still have a predictive theory for quantum gravity. And the basic idea, of course, is that we have a UV fixed point, as we can, like as I show you schematically here in this blue curve, where we just where the couplings don't go to infinity in the UV, but we get to a finite value. And this fixed point could have, if it has a finite dimensional UV critical surface, it could be predictive enough to predict all of these undetermined couplings that we see in perturbation theory that are generated by these UV divergences, and therefore give us a well-defined theory again. But as you see here, I show you two graphs here. The blue one is the standards or like a schematic asymptotically safe running coupling. But there's like one slight issue here, namely that we need some sort of sensitivity to power law divergences in order to see such a fixed point. And in particular, if you would start from minimal subtraction, which is this red curve here, then Newton's coupling in 4 dimensions would not get any sort of divergences that are required to renormalize it. And therefore, the minimal subtraction beta function is simply given by its mass dimension, by the mass dimension of Newton's coupling. And therefore, it's just 2 times g. And therefore, Newton's coupling will just blow up at some point. It will never hit a fixed point. So, of course, this is more or less well known, but I just want to like underline the fact here that we need some sort of sensitivity to power law divergences to obtain a fixed point. And of course, in functional normalization group, this is basically built in because there we have some sort of mass-like cutoff in the theory. And we have very naturally some sort of sensitivity to power law divergences. But in this talk, I want to ask whether we can also do this in perturbation theory and have some sort of perturbative scheme in which we have a UV fixed point. And this is motivated by like different facts. Of course, we all know that while the FRG is very powerful in the sense that it's non-perturbative and sensitive to power law divergences, there are also some more subtle questions related to gauge invariance or quantum diffeomorphism invariance. And those questions are, of course, where perturbation theory could shine. And that's like, for me, enough motivation to try to see whether we can actually see something like a UV fixed point in perturbation theory. And of course, to do this, we would ideally like to have some sort of mass-dependent scheme or a scheme that's sensitive to power law divergences, but that also respects gauge symmetries. And one example or one scheme that does that in principle that has actually gotten some more recent interest in the last few years is the idea that you can use dimensional regularization, but not only include the poles that you find in 4 dimensions, but also in higher or lower dimensions. And this is in principle enough to see fixed point in gravity. And you can even do more than this. For example, you can see threshold effects in QCD that are coming from the fact that you have massive quarks in the theory. But in gravity, there's a slight issue that you really rely on the structure of the theory in 2 dimensions. And in 2 dimensions, gravity becomes topological, at least the Einstein-Hilbert term. And then it's slightly non-trivial what you do with that, because if you do naive perturbation theory, then you have already a 1/epsilon pole in the propagator. And in this talk, I will try to avoid this. So basically what I'm asking for or to get at in this talk is I want to try to find a scheme that is on the one hand gauge invariant, it is sensitive to power law divergences, and it should only really rely on a computation in 4 dimensions, so that I somehow circumvent having to look at gravity in 2 dimensions at all. And this, I will argue, is basically some sort of gradient flow version. And this will at the end lead me to the Ricci-flow in gravity. But before I get to that, I would would like to just explain to you a bit of the foundations of this, which come from the gradient flow approach in QCD. And so I just want to give you a brief overview here of what we know there. And so this idea of the gradient flow in QCD, as at least in the way that I'm going to talk about this here, it was introduced about a decade ago now by Martin Liescher in the context of lattice QCD. And the basic idea here that we apply is that we introduce some artificial flow time parameter t, which is bigger than or equal to 0. And we use this flow time parameter to somehow smear out or smooth out quantum fluctuations in our field configurations. So you could schematically view this as in these 2 plots here, that at some small flow time or vanishing flow time, we have a very divergent and strongly fluctuating quantum field. And then if you apply some sort of a gradient flow, which is, you can think of it as very similar as some sort of a heat kernel diffusion equation like this here, then this sort of heat kernel will smooth out your fluctuations, and you get a nice smoother field configurations compared to the small flow time behavior. And when you do this, of course, you see that, or you can understand that you basically smear out quantum fluctuations within a typical radius. So for example, you can see that you smear out these fluctuations within a Gaussian curve of radius square root 8t. And this shows us now already that we have some sort of massive parameter now entering the game that's really given by the flow time parameter. And thus you can also see that the mass dimension of this flow time parameter you can also see from this heat kernel-like diffusion equation, where this delta is some sort of Laplacian, alpha is just a parameter, and t is here in the derivative. So this tells us that t has mass dimension -2. And this already tells us that this gradient flow naturally has some sort of massive dependence or scale dependence that we don't really have in minimal subtraction, for example. Now, how do we actually set up this in QCD? So of course, in QCD, we start from our gauge fields. So A is, by the way, I'm suppressing color indices here. So that are just all suppressed as part of the vector fields here. And for every field A that we have in standard QCD, we now introduce float fields. These float fields are now depending on the float time parameter t as well as the position x as the standard gauge fields. And they are defined such that at vanishing float time, we just get back our standard quantum fields A. And now where the gradient flow actually gets its name from is the sort of smearing that we do in this gradient flow scheme. Namely, we define the time dependence of the smeared, or of the gradient flow version of the gauge field B by some sort of, I mean, it's still some sort of like heat kernel or heat kernel-like equation, but what we have here on the right-hand side is really just the gradient of the action and that we have in standard QCD. So we have my capital D and my G's are now just the covariant derivative and field strength tensors that are constructed from this float field. And with this, we can now in principle start to do gradient flow or analyze the gradient flow or how the gauge fields depend on this artificial flow time T. And we can also see that if we would expand this term here on the right-hand side to leading order, we solve it at leading order, we explicitly see that we get some sort of exponential damping factor, which is really like intuitively motivated by the sort of heat kernel-like diffusion that I mentioned before. And this really like should show us that we can expect some sort of like smoothing of our quantum fields. And also that this exponential factor, of course, will irregulate some. We will see that it will not regulate all, but it will regulate some of the UV divergences that we typically encounter in Feynman diagrams. And the typical objects of interest that we're interested in here are some sort of correlators at finite flow time. So in the end, we will just calculate any correlator or any operator that's defined at finite flow time. So it depends on this B field or the float gauge fields at finite flow time, and we calculate its expectation value in the vacuum. And this will now be non-trivial simply because we have a massive parameter T that's entering the vacuum expectation value here. Of course, to do such a calculation, we need we want to translate this idea of the gradient flow to Feynman rules. And the basic idea that we use to do this are Lagrange multipliers. So we started from the gradient flow equation before, or the flow for the gauge field, which is basically this green bracket here. And we can simply implement that into the path integral by using Lagrange multipliers. So these Lagrange multipliers will really enforce that the gauge fields exactly fulfill this flow equation. Of course, this also is supplemented then with the initial condition that at vanishing flow time, this float gauge field is the same as the standard quantum gauge field. And when you do this, you see now that your propagators have some sort of like, if you compare to standard QCD, you get like some slight modifications. The most crucial one is that every vertex, if you work in this gradient flow formalism, has now an additional dependence on the flow time parameter. So every vertex in principle has a different flow time parameter that I call here S and T, for example. And you can have now two different types of propagators. The first one is what we call a flow line, and this simply arises from the fact that we have now a quadratic term here. And if you expand this float action to first order here in the float gauge field. So we have a quadratic term in L and B, the Lagrange multiplier and the float gauge field. And if you now try to solve the free theory, you see that the propagator for this type of propagator is given by this form here. In particular, we don't have any sort of typical 1/p squared that we have from a standard propagator, but we simply have this exponential damping factor and a Heaviside theta function. So this Heaviside theta function really ensures that of the direction where this flow line flows to has a higher flow time T at the vertex where it flows into than the vertex where it started at, which is here the vertex S. And by the way, the vertex S here is the one where we have the L field, and T is the one where we have the B field. And we also get from the initial conditions, so remember that we require that the float gauge field at vanishing time is the same as the standard quantum gauge field. We then from that also get a modified propagator for the standard float gauge field. And this looks like this. So basically, we just have the standard propagator. Of course, there will be some sort of Lorentz structures like G menus floating around here. But we get some modification that's from this gradient flow formalism. And this is exactly this exponential of e to the minus t plus s times p squared, which basically could already have expected from solving this the flow equation at leading order in the coupling. And yeah, we get these like modified propagators. In addition to that, we also get, of course, from the float action, if you expand this right-hand side here, the green part to higher orders in B, you also get like new vertices. So at the end, if we work on this gradient flow formalism, we get the standard QCD vertices that are just derived from the normal action that we have still included in the path integral. But on top of that, we get new vertices that simply arise from this float action that we have here. And these are characterized, these new vertices, by each of them having one outgoing flow line that simply arises because each of these vertices must be proportional to the Lagrange multiplier. So that means we must have one outgoing flow line. And of course, they also depend on flow time parameter S. And as we see from the form of this action here, this is simply an integral that we integrate from 0 to infinity. Of course, in the end, we will actually not integrate to infinity because we saw that each flow line has this Heaviside function included there. So there will always be some upper bound here. But each of these new float vertices come with such an integration associated with them. But yeah, so this is a standard, like the Feynman diagram prescription or the Feynman rules that we can derive from this formalism. And then in principle, we can just like start to compute correlators. And this will basically show us why this will be useful for us here. And so in principle, we just start at leading order, of course. And this means at leading order, we just have like the one Feynman rule from this correlator. So this is just the float field strength tensor squared. And it has one 2-point Feynman rule. And if you then write down the first, or the only Feynman diagram that you can, so you get like the 2-point Feynman rule here, and you contract the two B fields for the propagator. This propagator just gives you something that's proportional to this exponential factor from the gradient float propagator. And therefore, we see that it's finite. So at one loop, we actually have like a finite result for this sort of correlator that we can compute. At high loop orders, this is not true anymore, that all your results are finite. You can, of course, write now many more diagrams like these two here. These are still finite because we have different vertices here on the top, but the bottom vertex here is still coming from this operator that is living at finite flow time. And each propagator that we can write down into this Feynman diagram now has still one exponential damping factor simply coming from this flow time being finite. So these two diagrams therefore are finite. But we can get a diagram like this where we do have some sort of UV divergences, and this simply occurs from the fact that we have a subdiagram here that has or depends only on vertices at vanishing flow time. So these like black vertices are always vertices that come from the normal QCD action, which are defined at vanishing flow time. And therefore, the two propagators that we have in here don't have any exponential damping and therefore lead to a UV divergence. But you can actually understand that within the gradient flow QCD, that all these UV divergences are renormalized by the coupling. So the standard coupling renormalization in minimal subtraction, for example, is enough to renormalize all of these divergences. And yeah, when we do this, we can now compute this correlator. And this is like one example plot where we see how this is calculated over different values of t. But what is really interesting for us here is that we can use this correlator to define some sort of gradient flow version of the coupling. And the basic idea that of what we do here is that we say, okay, I have my alpha and now go to some sort of gradient flow scheme and define this alpha gradient flow to be equal to this correlator E, which is just the square of the field strength tensor, with some factors of t to ensure the right mass dimension. And the factors of 4 pi, and 3 are really just conventional. And that just leads to the fact that at first order, we have alpha GF equals to alpha MS bar. So at first order, it is equivalent. But now at higher loop orders, I can calculate all these like additional corrections. And this really gives me some sort of relation between the gradient flow coupling and the minimum subtraction coupling. And this really defines a new scheme for us for this gradient flow coupling. And in particular, what's really interesting for this, what the scheme is, that it can first be computed in perturbation theory as well as on the lattice as well, because on the lattice you can also calculate this correlator of the field strength tensor squared independence of some of the flow time. But what we will mostly focus on here is that this resulting scheme that we find like this is now a mass-dependent renormalization scheme. And this simply arises from the fact that this flow time has a mass dimension of -2. And of course, you could even see in QCD already, if you would do full QCD with quarks at finite masses, that these finite masses show up as threshold effects. And in minimum subtraction, of course, these threshold effects would be simply ignored. But we could see that in the gradient flow scheme, these threshold effects are arising. And therefore, we have a scheme that is sensitive to those effects. And therefore, it's very natural, of course, to ask whether this could also be useful as a scheme in gravity, where we want to be sensitive to these power law divergences to see some sort of UV fixed point. And yeah, this brings me then to the next part, which is really going to be gravity now and the Ricci-flow. And we basically will see now that this mechanism that I very briefly explained to you in the gradient flow QCD can be more or less straightforwardly applied to gravity as well. And we can try to set up a very similar renormalization scheme in the end for Newton's coupling. And yeah, to get started with, of course, when we start with analogy from QCD, the analogous of the gradient flow diffusion equation is now something like the Ricci-flow, which was first introduced by Hamilton in the 80s and then used by Perelman 20 years later to prove the Poincare conjecture. And the basic idea is that we have now the metric, which is now flow time dependent, and its derivative is given by this Ricci tensor that we have on the right-hand side. And this, I mean, the most important, or the two most important things about this equation here is that it's covariant, and it smears out metric configurations in the similar way that we have for gradient flow QCD. And when we do this now, so we start with this Ricci-flow equation that we have here. But of course, we want to now try to see whether we can put this in some sort of perturbative formulation. And what we will do here is that we will assume that the cosmological constant is vanishing. And then we can expand our metric field just around a flat background, like this. And of course, this gives us or expanding on the flat background gives us the possibility to apply standards like Feynman diagram techniques that really rely on Fourier transformations. And we also see that if we expand the right-hand side around the flat background, we see really that we have the second derivative showing up here. So we have a very similar behavior as the gradient flow QCD, where we have at leading order this sort of p squared or heat kernel-like suppression in the floats metric. And the question, of course, is now, if we start with this Ricci-flow here, whether we can basically apply the same things as we did before. So whether we can define in QCD, and by that I mean whether we can define some sort of Ricci-flow version of Newton's coupling. And for this, we will be interested in calculating some sort of correlators at finite flow time. So by the way, from now on, all headed variables are variables that live at finite time flow time t. So they are always gradient flow or Ricci-flow version of certain fields. And two correlators that we'll be mostly interested in are these two here, namely, this is just the volume element at finite flow time t. And here the white one is the volume element with the Ricci scalar, both at finite flow time t. And basically, what we want to do now is see whether we can calculate those in this perturbative Ricci-flow formalism. And to go ahead with that, of course, we first want to discuss whether we can find Feynman rules again in the same way as we did for the gradient flow in the QCD. And the idea to go ahead with that is very similar, of course. Namely, we just take our Ricci-flow equation and we write it now into the action or into the path integral using a Lagrange multiplier. A slight or an interesting fact here is that we decided to use here the Lagrange multiplier as a tensor density. So in particular, you see that there's no volume element here in the path integral. And so this is chosen deliberately, and I'll show in a sec why this is might be useful for the Feynman rules that we derive from this. But first, let me just mention that starting from this gradient flow or Ricci-flow action in gravity, we get some sort of very similar modifications to the propagators of the graviton as we see in the QCD gradient flow formalism. And in particular, we get from the fact that this is quadratic, or that we have like some part that's quadratic in L and H here, a flow line which connects this Lagrange field L to the graviton H. And the structure looks very similar, at least the important structure, namely that we have some sort of Heaviside function here that dictates that this flow time t must be larger than the flow time s. And we, of course, have this exponential suppression here. Of course, we also have, since these are L and H are both tensor fields with two indices, we have a lot of indices floating around here. But these are just really like some sort of like tensor indices that you can factor out. And the important structure that we have from this Ricci-flow formalism are these Heaviside functions and the exponential damping. And very similarly, we also get for the graviton propagator an exponential damping function as well. So we have some sort of exponential that depends on both s and t and leads to the propagator to be exponentially suppressed at if the vertices are at finite flow times. And similar as in QCD, of course, we also get new vertices. So again, we have the vertices that come from the standard Einstein-Hilbert action of gravity. But now, in addition to that, we get new vertices from the float action, namely from expanding the Ricci tensor here to higher orders. And of course, it's not very surprising now that if we expand the Ricci tensor to higher orders, we in fact get infinitely many vertices, which is the same as what we also see in Einstein-Hilbert gravity. So we start with a 3-point vertex where we have one flow line outgoing, since we have always just one Lagrange multiplier field here. But we can have two gravitons coupling into this vertex, as well as 3, 4, and so on. So we get simply like an infinite number of vertices, which is just really the same as in Einstein-Hilbert on standards Feynman rules for Einstein-Hilbert gravity. And here I can also explain now why we choose this Lagrange multiplier field to be a tensor density. Namely, you can see that if I would have chosen this L to be just a tensor, then in the integral, I would have needed to have the volume element. And then if you expand the volume elements to get the vertices, the higher order vertices, you also get vertices that depend on this flow time derivative of H. And this would simply just lead to like a slightly more complicated Feynman rule structure that first doesn't even happen in QCD at all. And in principle, you could work with this still, but it's just slightly more complicated. So we chose here to avoid this. And the way to do that is just by saying that this L is just a tensor density. And therefore, we can avoid writing this the volume element into the integral here. Now, some slightly technical remark that I want to make here concerns the gauge fixing and BRC invariance. I just want to mention that since one of the requirements that I wanted to fulfill here is that this gradient flow formalism or Ricci-flow formalism that I employ here for gravity is really BRC or gauge invariance. And in practice, it is really useful to have some sort of, even for the Ricci-flow part itself, a gauge fixed version of it. And you can actually like fix the gauge of the Ricci-flow by a technique that's very similar to the QCD gradient flow. And the idea is simply that you do some sort of gauge flow time dependent gauge transformation. So we just say that our float metric here is transformed into a like by a diffeomorphism transformation, with psi now being t dependent, and the t dependence is explicitly given here. So we get some sort of t dependence where we have a gauge fixing parameter alpha naught and a functional f that's in principle arbitrary. In practice, we will use it or choose it to be a very similar form as the standard gauge fixing and the Dondal gauge fixing of gravity. And we can work with that. What's important to know here, or one reason why this gauge fixing is useful is that, or the sort of gauge fixing is useful is that gauge invariant objects, so in particular the correlators that I want to calculate, are invariant under this gauge fixing. And that's simply because the only reason why this is some sort of gauge fixing is because it's a t-dependent gauge transformation. But anything that's not depending on a derivative of the float time is just invariant if it's a diffeomorphism invariant object. And therefore, these like correlators that we're interested in are also by construction invariant under this. But what this gauge fixing does for us is that we can introduce some gauge fixing parameter into the Ricci-flow action here. So before we simply had the Lagrange multiplier here and the Ricci-flow. And we now introduce also a gauge fixing that's proportional to alpha naught, and we can use this to in particular simplify the Feynman rules that we have for the flow lines, for example, and also for the vertices, of course. But of course, when I introduce such a gauge fixing, I also want to understand whether this the whole theory is still BRST invariant. And to do this, I mean, we know that the theory at vanishing flow time, because all the modifications that I introduced in the Ricci-flow formalism are at finite flow time. So at vanishing flow time, I still have a BRST invariant theory, and I can look up the standard BRST transformations of the graviton and the Faddeev Popov ghosts, which are here. And I can verify that my Einstein-Hilbert action with the Faddeev Popov gauge fixing are still invariant under this. But now I want to find some sort of BRST transformation that also holds at finite flow time. So starting from the unflowed metric or the metric fluctuation, I want to know what the BRST transformation is of the float metric. And in particular, since this float metric generally depends on t, the right-hand side will depend on t as well. And since the right-hand side must be related to the Faddeev Popov ghosts, simply because at a vanishing flow time, we know that this is the form of the BRST transformation. I know that on the right-hand side, I also need some sort of float Faddeev Popov ghosts now to have some sort of t-dependence here. And similarly, we see that so now if we have some sort of float Faddeev Popov ghosts, we can see that the BRST transformation from this at finite flow time also implies that the BRST transformation of the Faddeev Popov ghost at finite flow time also has the same structure as at vanishing flow time. But what's important to note here is that in principle at vanishing flow time we also have an anti-ghost field. But this is only, or the BRST transformation of it only depends on other fields that we only have at vanishing flow time. And therefore, we do not actually need some sort of anti-ghost field at finite flow time. So simply, we do not need to include a BRST transformation for this. What this tells us is, in order to achieve some sort of BRST invariance of this Ricci-flow action, we do need now a float ghost field, and by an initial condition, it's simply given as at vanishing t, it's simply given as the standard Faddeev Popov ghost. And then we basically have the freedom now to choose some sort of diffusion equation for the float ghost fields that we have to choose such that the resulting action is BRST invariant. But as I said already, these like float anti-ghost fields are not really necessary in this procedure. Now, if you work out all the algebra, and this is slightly complicated, and I'm just like showing you here like from completeness what you get from this, is like the resulting float action for the ghosts and for the graviton. So this is what we've seen before. And this is what we get for the ghosts. These two together can conspire such that we have BRST invariance. And again, you don't need to like exactly understand the details in this equation since they're like relatively long. And also like you can work out the BRST transformations of the Lagrange multipliers. So we have the Lagrange multiplier for the graviton here. And since we have now this float ghost field, we also have a Lagrange multiplier for them, which we call D here. And then you can work out that their BRST transformations is given by this slightly complicated expression. But yeah, the most important point is that when you do work out all this algebra, you can verify that the underlying action at vanishing flow time is BRST invariant, but this is just the standard result from quantizing Einstein-Hilbert gravity. But we also see that the float action, so this graviton flow action and the float ghost field, the float ghost action are together invariant under BRST transformations. What's also important though is that I've argued now or shown you that together with these float ghost fields, we get an invariance in BRC transformations. But it turns out that we actually don't really need these float ghost fields in practice. And the reason for this is that we will only ever be interested in correlators that have no external ghosts, right? Like the correlators that I mentioned before simply involve the volume element, for example, or something like the Ricci scalar, which only depend on the graviton field, but not on any ghost fields. And therefore, any float ghost that I get in the Feynman rules from this can in any Feynman diagram only ever appear to start from a float vertex. And it can also only end at another float vertex simply because there's no other vertices that the float ghost can connect to. And what this leads to is simply that you always get some sort of closed ghost loops, but these are now float ghost loops. And an example is given here, which is simply like the easiest example you could think of. But the important part that we have to make here is that remember that these float lines always come with Heaviside theta functions. And while these two vertices here come with like integrals over the float time parameters S1 and S2, simply because this comes from the float action, we see that the whole part or this whole subdiagram must be proportional to a structure like this, where we have the integration over S1 and S2 and two Heaviside functions, which force on the one hand S1 to be bigger than S2 and S1 also and the other way around. And so because of this, we can see that this float ghost loop actually vanishes. And therefore, all float ghosts that we could include here in the theory vanish by construction because they always will lead to some vanishing loops, flow line loops in the theory. And this basically tells us that while it's important to check that we have some sort of BRST invariance if we include these float ghosts, we actually can work simply with without ever touching float ghosts and can only work with the graviton and the float version of the graviton and the standard for DF pop of ghosts at vanishing float time. I do want to make some quick remarks about the renormalization now, because in principle we have now the Feynman rules and can start calculate our correlators to see what we get from them. And yeah, as I mentioned, I'm particularly interested in those two correlators, so the volume element and the volume element times the Ricci scalar. And similar as in QCD, we can very easily see that at one loop, everything is finite simply because each propagator that we get here has an exponential damping factor. So at leading order, we don't get any UV divergences. This is not true anymore, though, once we go to higher orders. So from two loop onwards, we are starting to get UV divergences. And I want to explain quickly, like in what kind of form these arise. First, I give you like three examples here. The first one is actually UV finite still, and this is very similar to a diagram that I showed you before in QCD. And the reason why it's UV finite is that all of these three propagators are connecting one vertex at finite flow time t, which is coming from the correlator that we calculate at flow time t. And therefore, these exponential damping factors kill all UV divergences in this diagram, and we get a finite result. But this is not true for these other two diagrams here. And the reason is simply, again, that we get subdiagrams that are constructed from these vertices that come from the standard Einstein-Hilbert action. So they live at vanishing flow time. And because these two vertices here are at vanishing flow time, the propagators that we have here connecting them don't have any exponential damping factors and therefore are simply UV divergent. In the same way as in the underlying theory of Einstein-Hilbert gravity. But of course, we know how to renormalize them. And in contrast to QCD, those divergences here do not get renormalized by the coupling, namely the Newton coupling in the theory. But instead, these are the off-shell divergences that we remove by field redefinitions. So those divergences that we encounter here, and this applies, of course, to all such UV divergences that really come from the theory at vanishing flow time, they are all removed by a field redefinition of this form. So we just like transform the metric to absorb these UV divergences. But in addition to these like UV divergences that we have standards of coming from subdiagrams of the unflowed theory, we also get some UV divergences that are new and genuine to the gradient flow formalism or the Ricci-flow formalism here. And an example is given here on this diagram on the right-hand side, where we have two flowed vertices here. And you might think now that this diagram must be finite and have not any UV divergences because simply these vertices are at finite flow times, and the propagators have exponential damping factors. But the problem is that we integrate those vertices or the flow time parameters of those vertices from 0 up until an upper bound. And because we start at 0, we actually do get some sort of UV divergence from the lower region of integration. And therefore, we do have some sort of new UV divergences that are encountered at the border of the integration region. And then, of course, you can ask yourself, what do we do with those? Because we do have to renormalize these new UV divergences as well. But you can actually see that the structure is very similar to the standard UV divergences that we have coming from those diagrams here. So comparing these two diagrams here, the only difference really, or the only relevant difference here is that in the left diagram here, we have always just graviton propagators. So we have an H field coming from the vertex, an H field coming from this vertex, and then an H field coming from the other side of the operator as well, and the vertex here again. What's different here is that we have a graviton propagator here, so two H fields. But here we have the graviton flow line. So we have the Lagrange fields connecting to the graviton of this operator Feynman rule. But you can actually see that since the graviton couples to the Lagrange field as well as to itself, we can actually renormalize this by the same counterterm structure as we used to renormalize this diagram here. And we can therefore simply use like a counterterm that has two external H fields to remove this divergence. And then in any diagram where we have a subdivergence of this form, we can also insert the same counterterm to remove this divergence as well. And what this tells us is that both the old divergences or the divergences in the unflowed theory of gravity, as well as these new divergences that are induced by the Ricci-flow formalism, can be removed by the very same counterterms, namely these field redefinitions that we use. And we actually use this now to, or we can use this to renormalize the Ricci-flow of gravity here in general at the second loop order. And how we do this in practice is we impose a renormalized initial condition for the flowed metric. So if we remember some setbacks, I just said, oh, this should, by the way, be t equals 0 here on the left-hand side. But I introduced before the flowed metric field at vanishing flow time such that it should be equal to the standard metric. But we can renormalize this initial condition by some new counterterms to remove exactly these UV divergences that we encounter that are simply coming from these offshore divergences and are related to field redefinitions. And the counterterms that I include here then are simply given in this form here. So that we have the standard Ricci scalar times G mu and Ricci tensor mu terms with C1 and C2 would have to be determined by computation because these C1 and C2 now include both the divergences from the theory at vanishing flow time, so the standard divergences that we can check in the literature, as well as new contributions from the Ricci-flow formalism itself. And when you do this, you get some result, which is given here. So we determine both C1 and C2 unambiguously. And we actually have checked that this is sufficient to renormalize all the gauge invariant operators that we are interested in at next to leading order or second loop order. There's a small side remark here, namely that we exclude BST exact operators. And this is relevant if you, for any reason, would be interested in computing a correlator of something that's not diffeomorphism invariant. But as long as you only consider diffeomorphism invariant objects, these potential other divergences that are in the form of BRST exact operators drop out and will not lead to any divergences of diffeomorphism invariant correlators. And yeah, with this, we can actually like go to the results now. And I just want to briefly mention this, the computational setup that we use to do this, and I also show you here some like example Feynman diagrams. So the setup that we use.
Sorry, Yannick, to interrupt. So you're 45 minutes in. If you could wrap up within the next 10-ish minutes, that would be great. Thank you.
Yes. So this two chain was originally developed for the QCD gradient flow, but basically we can immediately also apply it to the computation of our diagrams here. And it simply is like a chain consisting of QGraph to generate all the diagrams. Then we use tab here, X to translate this to form notation, and form is used then to introduce or insert all the Feynman rules and deal with the tensor algebra. And then we use some sort of integration by parts identities implemented in Kira and Firefly to remove the resulting Feynman integrals to a small set of master integrals, which you can then solve analytically. And when you do this, the result that you get is given here. And here we still just compute everything in minimum subtraction. And the reason why it's relevant that we did this in minimum subtraction is because of the renormalization of the initial condition that I just mentioned before. And we get this result here for the volume element and the expectation value of the volume element and the Ricci scalar. And one important point that I should mention here is that we actually did this computation with open gauge parameters in the standard in the standard Dedonda gauge. So in principle, there could be some parameters alpha and beta showing up here, but these actually completely drop out. And therefore, we verify that our results are gauge parameter independent, which of course is a good cross-check of our computation. One other remark, though, is that these results are still mu-dependent. And you see that this L mu t is actually a logarithm of mu squared times t. So we see that our results are still mu-dependent. And this is simply an artifact of the fact that we have to renormalize UV divergences by field redefinition. And this is like a slight issue because in order to define a Ricci-flow coupling for Newton's coupling, we need to start from some objects that are mu-independent. And let me just briefly explain how we fix that. And the idea here is that we go away from minimal subtraction and go to a slightly non-minimal subtraction for our initial condition in the Ricci-flow. So we start again from our counterterms in the initial condition. And so we now can choose, in minimal subtraction, we would have only had this epsilon poles, which is what we calculated, what I showed you before. But in principle, we can also include higher order terms in epsilon. And these higher order epsilon terms, we can actually use to do something that's very similar to something called the ring scheme for float quarks and the gradient flow formalism for QCD. And what happens there is something very similar to here, because there you have quarks that need a wave function normalization. And this wave function normalization also induces some RG scheme dependence. But there you can fix it simply by like fixing an operator to basically a constant. And we do the same thing here. And this the way we do this is we take the expectation value of the volume element. And in the scheme that we call the fixed volume scheme, we simply fix this operator to its leading order value. So we only introduce these terms here that we cannot change by a non-minimal subtraction of these initial conditions here. And then this in this fixed volume scheme, this volume element is simply fixed to this value at all orders. But we do get still something non-trivial for this other operator, namely the correlator of volume element and Ricci scalar. And at next to leading order, we have this now very simple form. And this is now what we can use actually to define a Ricci-flow coupling. And the Ricci-flow coupling, or the way that we define it here, is simply as this. So it's proportional to the expectation value. And we choose now t to be equal to rho over mu squared. So we identify the flow time t in terms of the standard mu running that we have, or the mu parameter. And then we see that our beta function is given by this form here. So we have, of course, the standard canonical term, as well as a one loop correction, or we calculated this from a two loop procedure here, but it has the form of one loop beta function for Newton's coupling. And what's important here is that we have the right sign actually to see a fixed point. And I'm showing you here in the plot of what this beta function looks like. And of course, one question is, while we do see a fixed point, is this fixed point actually perturbative enough that can we trust it? And we see that the fixed point value here depends on this parameter nu, which is really like a convention at this point, because it's just like a parameter that we write in front of this expectation value here. And the question is that if you want G to be perturbative or G star to be perturbative, we should assume it to be smaller than 1, which translates into nu, or this new parameter being bigger than 1/5. And whether or not this is sensible or not is difficult, of course, to like say at this point in the results, because this is at this point just a one loop perturbative beta function. We can get some idea though if we compare back to the way that this operator looks at in the fixed volume scheme. And the point that I just want to make here is that basically, if you look into the numbers here, you have numbers of the order of 1 times gn over pi, and the same with the loop correction. And thus it makes it seems sensible to choose this gradient or the Ricci-flow coupling such that it is given as essentially gn over pi, which would mean that we should choose nu to be 1/4, because then we would simply factor out this factor of 3/4 in here. So we would get rid of this factor of 3/4, and we have at leading order just gn over pi still here. And this value of nu, which would be 1/4, is indeed bigger than 1/5. And therefore, with what we have here, we could actually say that it looks perturbative. But of course, this is not, it is still a bit speculative to conclude this here. Now, let me come to my summary. And yeah, I showed you hopefully well how we started, or how we implemented the perturbative Ricci-flow. And the basic idea is that we have some sort of smearing for the metric in terms of the Ricci tensor. And some like important points here are that this is really like smoothing out the metric configurations that we have in general. And it's fully BRST invariant, and it is sensitive to mass scales or power law divergences. And I also showed you that like any UV divergences that we encounter in this Ricci-flow scheme are renormalized by this initial condition. And by computing these like flow correlators, we also see that we can find a usable scheme for the Ricci-flow, or a Ricci-flow scheme for Newton's coupling, where we find perturbative, or it looks like a perturbative UV fixed point at this point. Of course, there's also many interesting questions we can go on from here, and one of the most crucial ones, I think, is extending this computation to next leading order, because then we can actually verify whether this fixed point remains and this seems to be perturbative. Other directions, of course, include also the inclusion of matter or the cosmological constant, which we have not included here at all yet. And what's also really interesting is the implementation of the Ricci-flow on the lattice, for example, in causal dynamical triangulations or Euclidean dynamical triangulations. But yeah, with this, I want to thank you all for your attention, and let me know if you have any questions.
Great. Thank you very much, Yannick.